In this video, we're going to do the remaining problems from the worksheet packet for AP Review Topic 9, which is over polars. So the first one that we did not do in class or in the other YouTube video was the problem from 2017. This was number 2. It was with a calculator. I'm going to grab my calculator here. Okay. Let's read it. The figure on the right shows the polar curves. R is equal to f of theta, which is this polar curve, and R is equal to g of theta, which is this polar curve. Okay, for 0 to pi over 2. 0 to pi over 2. This is definitely one that we're not familiar with that format. That's not one of our known polar curves that we learned about in pre-cal. This, however, is one of our known ones. This is a circle out on the x-axis of diameter 2, right? So this is our g of theta curve. Now, if for some reason you don't know that, or you have a brain freeze or whatever, and you're just not sure which is which, then go to your calculator, put it in polar mode and graph, just to see what the graphs look like, and then go right back to function mode. Okay? Be sure you're in function mode for all of your computations. All right? Okay. Let R be the region in the first quadrant bounded by the curve f of theta and the x-axis, and let S be the region in the first quadrant bounded between the two curves and the x-axis. Okay. First of all, we're supposed to find the area of just R. Well, the area of R does not even need that g of theta. The area of R only relies on the f of theta curve, right? So the area of R will be the integral from theta equals 0 to theta equals pi over 2, right? And again, if you're not sure about that, put in theta equals 0. Put theta equals 0 here. Cosine of 0 is 1. 2 times 1 is 2. So I know I'm starting there for that curve. Over here, sine of 0 is 0. Cosine of 0 is 1. But f starts at 1, which is right here. So when theta is 0, r is 1. So this is where theta is 0 here. Okay, so 0 to pi over 2 of just our R curve. So it's 1/2 of, just our F curve. 1/2 of, and if you want to, you can rewrite this out, or you can use, they were nice enough to give us F and G, so we could just say F of theta squared. You could even just say F squared, and that's fine. Don't forget your 1/2 d theta. And then that goes in our calculator. And now in your calculator, I'm going to put my F equation in for y1 with x representing theta, and I'm going to put the G equation in for y2. All right? So 1 minus sine x cosine 2x. 1 plus. Ooh, I'm glad I caught that. So I always go back and make sure I'm putting these in right. So make sure, I always do that. Even then, sometimes I miss something, but do your best not to mess that up. Okay. And then in my home screen then, I just need the integral from 0 to pi over 2 of 1/2 of y1 squared, right? y1 squared d theta, x is theta. So I get 0.648. 0.648. So that question was worth 2 points. 1 point for the integral, 1 point for the answer. So the integral was all or nothing. The answer was all or nothing. Okay? So if you missed the 1/2 here, you didn't get credit for the integral or the answer, because your answer wasn't going to be right either. Okay, so make sure you get your formulas right. All right, part B. The ray theta equals k, where k is between 0 and pi over 2, divides S into two regions of equal area. Write but do not solve an equation involving one or more integrals whose solution gives the value of k. So first of all, there's this ray. It's theta equals k. So remember, theta equals k goes through the origin, right? And it's a line something like that, right? This ray divides this S region into two regions of equal area. So I know my ray is going to be somewhere over here because the curve is thicker here and thinner there, so it's going to be somewhere over there. So the ray is going to look something like this. I'm just going to do it dotted in case I need to see what I'm doing later on. So that's like theta equals k. All right? So I need an equation that would find k, knowing that these two areas are equal. So there are different ways to do it. I'm going to do it this way. I'm going to say the integral from 0 to k, of the entire area, that would be to g of x, right? The entire area minus this inner area, because we only want S involved. We do not want R involved. So the g of theta graph minus the f of theta graph, right? So it'll be 1/2 g of theta squared minus 1/2 f of theta squared d theta. So that would be the area of S between those. It's just between the two curves, right? And that has to equal the integral from k to pi over 2 of the exact same thing. K to pi over 2 of the exact same thing. Okay, so that's one equation that will work. There are other equations that will also work, but the inside is always going to be the same. The inside will be the same. Okay, this was worth 2 points, 1 point for the integral expression, and 1 point for an equation that will work, the equation. Okay, we could have also said like from 0 to pi over 2 is equal to twice the integral from 0 to k, or something like that. All right, for each theta between 0 and pi over 2, let w of theta be the distance between the points f of theta, that's r theta, and g of theta, that's its r theta. So w is the distance between the two curves, okay? Write in the expression for w. So first I'm going to write an expression for w. So w is just the distance between the two curves. So like from here to here. So that will be w. So outer minus inner. Outer minus inner. So w of theta is equal to the outer curve, which is g of theta, minus the inner curve, which is f of theta. And I could write what each of those is, but I don't have to because they very nicely named them g and f for me. Okay. Now I want to find, not just write the expression, but actually find w sub a, which is the average value of w over the interval from theta 0 to theta pi over 2. So the average of w, and they tell me to name it w sub a, will equal, and they're asking me, do I know the formula for the average value of any function? And I do. It's 1 over b minus a, 1 over b minus a, integral of, from 0 to pi over 2, from a to b, of whatever I'm averaging. And I'm averaging w, right? So that would be the average W, and I need to find it, so I need to stick that in my calculator. Okay? So in my calculator, and for my y equals, I'm going to, I think I'm going to go ahead and put g minus f, so y2 minus y1, and then I have that in there. And then in my home screen, I can do 1 over pi over 2. 1 over pi over 2 is 2 over pi times the integral from 0 to pi over 2 of my y3, right? Of my y3. So a second. So 0.485. Okay. And that's all I needed for that. So this problem was worth 3 points. 1 point for your W of theta expression, 1 point for the integral for the average value, and then 1 point for that average value, the answer. So 3 points. Okay, next up, using the information from part C, find the value of theta for which W of theta is equal to W sub A. So we want the theta that makes W equal this, right? So that's not bad. I just take W and set it equal to 0.485, right? So W of theta is equal to the average value of W at theta equals, okay, to my calculator I go. So this is my W sub A. I don't want to lose that, and I don't want to chop it to 0.485 because I might not, my final answer might not be correct to 3 decimal places. So I want to store that number in for something. I think I'll store it in for A. Okay. Now I'm going to go use it because I'm going to be setting my y3 equal to that A value. So I'm going to turn off the graph for y1 and turn off the graph for y2. I'm going to get rid of this thing. And up here I'm going to put my A value. Oops. Oops. I keep doing that. Okay. So if I graph these two and find where they intersect, I'll be finding that theta value. Okay. So I know I need between 0 and pi over 2. And then I just need to include that theta value, and theta value is close to 0. It's about a half. Negative 5 to 5 will indeed include that, so I think I'm just going to leave it there. Probably don't need all the way from negative 5 to 5, but I think it'll work. So that was the W curve, and that's that curve, and it is hard to see this. It is hard to see. I'm going to come and do negative 1 to 2, and that'll be a little bit better anyway. So there's my W curve. There's my W curve, and there's the point for whatever. So second calc 5. For intersection, enter, enter, enter. And this will give me where they intersect at. So this, remember, x is your theta. So that's your theta value that these two are equal at. So 0.517 or 0.518 if you round up. So 0.51, I like to round, so 0.518. Okay. So that was that part. And then it says, is the function w increasing or decreasing at that value of theta? Well, w is increasing or decreasing. That, we need the derivative of w for that, right? So w prime, I need w prime at that theta value, right? Well, I have w, it's in my calculator. I already said what it was. So I can just let my calculator find that value. So in my calculator, my calculator still thinks x is that number. And if I come over here and type in x, it still thinks that's the value of x. If I did 2x, it would multiply that by 2, okay? So in my calculator, the calculator right now has this value stored in for x. If you like, you can go store it in for another variable, but right now my calculator thinks that x is that number. So I'm going to take the derivative, math 8, of my what I have in for y3, so y3, that's the w function, and I'm evaluating it at what number? Well, the number is x. Again, if you want to go and put it in for a or something, that's fine. You're going to get the same answer here. I know this looks a little confusing, but the calculator reads a variable where it needs to read a variable, and it reads a value where it needs to read a value. Okay? Here it's looking for the variable. This is the variable, this is the value. Okay? Anyway, all right, so negative 0.582, which is negative. Therefore, w is decreasing at theta equals 0.518. Okay? So this part was worth 2 points. 1 point for solves w of theta is equal to the average value of w, and then 1 point for the answer to that next question with reason. Alrighty? Okay, the next problem that I'd like to do with you is the problem from 2013. This was number 2. It again was with a calculator, so we'll keep our calculator out. The graphs of the polar curves r is equal to 3. That's a circle centered at the origin of radius 3. And r is equal to 4 minus 2 sine theta. That's a limacon with no loop. Are shown in the figure. The curves intersect where theta is pi over 6 and theta is 5 pi over 6. That's awfully nice. I'm going to draw those in. So they gave us that. Otherwise, we would have to go and find that. So pi over 6 and 5 pi over 6. Okay. Let S be the shaded region that is inside the graph of r equals 3 and also inside the graph of r is equal to 4 minus 2 sine theta. Find the area of S. So this is the shaded region. So first let's get this region. Okay, let's get this region. So we're going from pi over 6 to 5 pi over 6. Remember that you can only go counterclockwise, so we have to go this way. We can't go that way, we have to go this way. So we're starting at pi over 6, and we're ending at 5 pi over 6. Okay, and then which curve are we going to? Which curve are we going to here? What is that curve? Well, that is the little limacon with no loop, right? So that was our 4 minus 2 sine theta. So the integrand for that piece will be 1/2 4 minus 2 sine theta squared d theta. So this integral will give us that area. Now we need the other area. It's a portion of a circle, right? The question is which portion? There are a couple different ways we could do this, but I think we're just going to do it with an integral, okay? So we're adding that other area. My question is, where do we start and where do we stop? Well, we can only go counterclockwise. So we cannot start at pi over 6 and go this way, all right? We have to start at this one. So I'm starting at 5 pi over 6. I'm starting at 5 pi over 6, and I'm going this way. And my question is, where am I going to stop? Should I name that stopping point pi over 6? The answer is no, because look, we'd be going from pi over 6 to pi over 6. We'd be going backwards, and we don't want to go backwards. That would be taking us this way, right? So don't do that. We need to go all the way around. If we go all the way around, when we get to here, we're at pi. When we get to here, we're at 3 pi over 2. When we get to here, we're at 2 pi. We need to go beyond 2 pi, another pi over 6 units. So I need 2 pi plus pi over 6, and that is 13 pi over 6. That's where I need to stop. Okay? And then for that integrand, I'll need 1/2, and we're going to the r equals 3 squared d theta. So this is the expression that will give the area. We are told to find the area, not just write the integral expression that gives the area. We have to actually find it. So this is not a safe stop spot. We have to go put in our calculator. I think I don't really need to put that 3 in my calculator, but I think I'm going to put, let me get rid of all this. I think I'm going to put this other one in my calculator in for y1, because in these types of problems, they usually play more with the more involved integral expression, r value, than with a plain old 3. Okay, so now I'm going to come put this in. So I have the integral, math 9, from pi over 6 to 5 pi over 6 of 1/2, and that is my y1 squared. y1 squared d theta. My x is my theta value. Plus, and now I need the integral from 5 pi over 6 to 13 pi over 6 of 1/2 of 9. So I got 24.709 or 8 there, right? So 24.709. I like to round, okay? They gave 3 points for this. 1 point for the integrand, 1 point for the limits and constant, and 1 point for the answer. Okay, next up, we have a particle already. So this is now a particle motion problem. A particle moves along the curve so that at time t seconds, theta is equal to t squared. Theta is equal to t squared. Find the time t in the interval from 1 to 2 for which the x coordinate of the particle's position is -1. Okay, we want the x coordinate to be a -1. Well, I know what to do for that. I know that x is equal to r cosine theta, right? So our r is 4 minus 2 sine theta. So x will be that expression, right? And now they told me that we're looking for t, so I need to get t involved. I want to get rid of the theta and get t involved. So they told me that theta was t squared. So x must also be 4 minus 2 sine of t squared cosine of t squared. And that's what I want to set equal to -1. And now I can just go and use my calculator. I want to find where this equation is equal to -1. So in my calculator, I'm going to turn off this graph and type in this whole thing here carefully, right? So parentheses, 4 minus 2 sine t squared, my x is going to be t now, times cosine of t squared. And then here I'm going to put a -1. And for my window, I know that t is between 1 and 2, so that's all I want to see, 1 and 2. That's it. For my y, I just need to include -1. So I'm going to include -1. I think I'm going to go from like maybe -3 to 2 is fine. That'll include -1. Okay? And we're just looking where these two graphs intersect. So second calc 5, enter, 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 and I'll get the intersection point there. They intersect at t equal, x is now my t, right? T is equal to 1.428 or 427. Okay. So, an odd little problem, and this is something that I could never prepare you for in advance, and you're going to see things like this on the exam, where you just have to use your head and use your knowledge and see what you can do with it. Let's see how they scored this. They gave 1.4 x of theta or x of t. So, even if you just wrote this, you got that point, okay? 1.4 setting either x of theta equal to -1 or x of t equal to -1. I set x of t equal to -1. So either one of those, you got a point. And then the last point was for the answer. So hopefully you got at least 2 of those points, right? Okay, for the last section here, the last part of this problem, for the particle described in part B, find the position vector in terms of t, and then find the velocity vector at time 1.5. Okay, so for this particle, I want it in terms of t again, right? So in terms of t, I already have the x coordinate in terms of t. It's right here. So x is equal to 4 minus 2 sine of t squared times cosine of t squared. And y will equal, y is our sine theta, right? So the r will stay the same, except I'm going to put t squared again in for theta, and then I need sine of theta with t squared in place of the theta. So the position vector in terms of t is, I'm going to write it in vector notation, 4 minus 2 sine of t squared cosine of t squared, comma, 4 minus 2 sine of t squared, sine of t squared. Close the vector notation. Okay, that's the position vector. Now we want to find the velocity vector. Well, I need to say what I'm doing. So the velocity vector at time 1.5 is equal to x prime at 1.5, comma, y prime at 1.5. So we're using our knowledge of vectors here too. So this, what started out as a polar problem, did a really, really good job of combining polars with parametrics and vectors here. Okay? This goes to show you what they can do. Okay, now I want to go ahead and evaluate this. So I need x prime at 1.5 and y prime at 1.5. So in my calculator, remember in my calculator, in for y2, I have my x of t. In for y2 is my x of t. So on my home screen, I can take the derivative of my y2 at time 1.5, and that will give me this first coordinate, negative 8.072. And now I need to do the same thing for y, so it's going to be the easiest for me to go back up to my y equation. This is the last part of the problem, so I'm just going to go and change this. I'm going to zoom over and I want to replace cosine with sine, right? So that's a quick replacement there. Now back to my home screen, and now I need that exact same thing, so I'm just going to scroll up, grab it, and now this will be my y prime at 1.5. So negative 1.673. Okay, that was worth 3 points. 2 points for the position vector, 1 point for the velocity vector. Really am always so impressed with their creativity when it comes to creating problems and how they can combine different topics. It's very impressive to me, and it makes it fun to me too to challenge myself. Know that when I look at these, I haven't seen these in so long, so it's like I have, and I forget a lot. So it's fun for me to do this. I hope it's fun. Okay, next up, let's take a look at the problem from 2007. This was number 3. Back in 2007, number 3 was also with a calculator, so we have a calculator at our ready here. The graphs of the polar curves r is equal to 2, another circle centered at the origin. And r is equal to 3 plus 2 cosine theta, another limacone with no loop. R shown in the figure on the right. The curves intersect at 2 pi over 3 and 4 pi over 3. If they hadn't given us that, we would have set those equal to each other and found it on our own. But since they gave it to me, I'm going to go and draw those in. It'll help me. That's 2 pi over 3, and that's 4 pi over 3. Okay, let R be the region that is inside the graph of r equals 2 and also inside the graph of r is equal to 3 plus 2 cosine theta, as shaded in the figure on the right. Find the area of R. So this is very similar to the problem that we did. I forget if it was the last one or the one before. They're getting confused in my mind. But anyway, we can find this area, right? So first of all, I'm going to do this area first. So I'm going to start at 2 pi over 3 and end at 4 pi over 3. So 2 pi over 3 to 4 pi over 3. And then my integrand will be 1/2, don't forget our 1/2, 1/2 of that r squared. Well, that r is the limacone. So that will be our 3 plus 2 cosine theta. And then we don't forget to square that because that's part of the area of a sector. And then we don't forget our d theta because that is also the area, part of the area of a sector. Okay? So that will give us this shaded area. Now I need the rest of the shaded area. So plus, I'm adding that on. Okay, let's be careful here. There are a couple different ways we can do this, but we cannot start here and go clockwise. Can't do it. We have to start here. So I'm going to start at 4 pi over 3. Starting at 4 pi over 3. And then I want to go around past 2 pi all the way to 2 pi over 3. So that would be 2 pi plus 2 pi over 3, right? So that would be 8 pi over 3, and that would work. 8 pi over 3. So just like in the problem that we did recently, you have to go past 2 pi and keep on going. The other way that we could have done this would just be going from 4 pi over 3 to 2 pi and then doubling it, because there's symmetry here, right? That would work as well. You can definitely do that too. So the integrand will be 1/2 of that r squared, and that r is just r2 d theta. So that's the integral expression that gives the area, and now we have to actually go and find the area. So we're going to find it, clear out what's here, clear, 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 all that stuff that we had for the last problem. And I'm just going to, and for y1, I'm going to put 3 plus 2 cosine theta. It'll just keep me from rewriting that all the time. So there's my y1 here. So integral 2 pi over 3 to 4 pi over 3 of 1/2 y1 squared d theta. Oops, well, that was just that piece. Now I'm going to add to that piece integral 4 pi over 3 to 8 pi over 3 of 1/2 of 4. Well, 1/2 of 4 is just 2. I think I can do that. So the combination of those areas is 10.370. 10.370. Okay, and again, we had to actually find it. It said to find, not just write the integrals, but actually find it. So don't say stop with just the integrals. That's not a safe stop spot. This was worth 4 points. 1 point for the area of the circular sector. That would be this one. 2 points for the area, for the integral for section of limacon. That's how they said it. That was 1 point for the integrand, 1 point for the limits and constant. And then 1 point for the entire answer. So 4 points. That's how they split that up back then. I noticed that it seems to me like these earlier years, sometimes they got more detailed on how they gave points. Anyway, okay, part B. A particle is moving with a non-zero velocity along the polar curve given by that limacon. And it has position x of t, y of t at time t with theta equals 0 when time equals 0. Well, that's convenient. That means we're starting like right here. We're starting there. Time 0, theta 0. I like that. Okay, this particle moves along the curve so that dr dt is equal to dr d theta. So again, it's kind of like t and theta are very similar to each other. They are acting the same, okay? Find the value of dr dt at theta equals pi over 3, okay? And interpret your answer in terms of the motion of the particle. Okay, well, I know what r is. R is equal to 3 plus 2 cosine theta, right? I want dr dt, right? I want dr dt. And I want to evaluate it when theta is pi over 3. They tell me, though, that dr dt is always equal to dr d theta. So this is equal to dr d theta at theta equals pi over 3. And that's something I can find in my calculator right now. So that's something I can find. Dr d theta, so math 8 for derivative. My x is theta, and this is what I have stored in for y1, right? So y1 evaluated at pi over 3. Negative 1.732. So that is the value of dr dt when theta is pi over 3. Okay? And now I need to interpret that answer in terms of the motion of the particle. Okay, so what does that mean? So as the particle is moving along this curve, at pi over 3 would be around here. At pi over 3, I have that dr dt is negative 0.1732. So that means that at pi over 3, since dr dt is negative, at that time, which is at that theta, the particle is getting closer to the origin at a rate of 1.732. So that's what I'm going to say. So at theta equals pi over 3, the particle is moving towards the origin at a rate of 1.732. Okay? This was worth 2 points, 1.4 dr dt at theta equals pi over 3, and 1.4 that interpretation. Okay. For the particle described in part B, dy dt is also equal to dy d theta. So just like dr dt was, so is y. Find the value of dy dt at theta equals pi over 3 and interpret your answer in terms of the motion of the particle. Okay? We need to get y involved. Well, y is equal to r sine theta, right? So y has to be equal to that curve, 3 plus 2 cosine theta, sine theta. Okay? I want dy dt, but it's going to equal dy d theta. So dy dt at theta equals pi over 3 is equal to dy d theta at theta equals pi over 3, which is equal to, all right, here we go. I need the derivative of this right here, which is y1 times sine of theta. That's what I'm taking the derivative of, and I need the derivative at pi over 3. So here it's going to be 0.5, right? 0.5. Again, there's a little numerical error, numerical method error here to this derivative, but it would be exactly 0.5 if we did this by hand. So 0.5, and now that is dy dt at theta equals pi over 3. And now we need to interpret this answer in terms of the motion of the particle. So dy dt is 0.5, it's positive, right? So that means here the particle is moving in the positive y direction, so the particle is moving up. And it does look like it's moving up, doesn't it? It is moving up. It's moving up and to the left. So if we were to find dx dt here, I'm sure it would be negative because we're moving to the left. So at theta equals pi over 3, the particle is moving upwards, which is also away from the x-axis. Okay, at a rate of 0.5. they did not tell me to use units, so I won't, but that would be units per whatever their time unit was in, okay? So this answer was worth 3 points. It was 1 point for the expression for y in terms of theta. So that was worth 1 point, okay? 1 point for dy dt at theta equals pi over 3. So that was the 0.5. And 1 point for the interpretation. Alrighty? So get every point you can. Even if you don't know really where you're going with it, I'm pretty sure you guys could have gotten that point, right? And then I think you could have gotten the derivative. You would have had to say that it was dy dt, I guess, but anyway, get everything you can out of these. Okay, let's take a look now at the polar problem from 2019. This was number 2 with a calculator. Let S be the region bounded by the graph of the polar curve. R is equal to this. This is definitely not one of our known polar curves from pre-cal, right? For theta between 0 and square root of pi, okay? So 0 to square root of pi. And if you are not confident that it goes in that direction, go ahead and plug it into your calculator in polar mode and quickly see that it does go there. We start at 0, we start theta equals 0, and the curve goes this direction, okay? First of all, we want to find the area of S. So just the area. So the area of S will be the integral from 0 to square root of pi. Nothing tricky going on. We just have the one curve, right? And it'll be 1/2 of that r squared d theta. And since there's only one r here, you can just put r squared d theta. There's only one r, so you're safe in doing that. Okay? Actually find the area. So let's find the area here. I'm going to put that carefully in for my y1. So 3 square root of theta, my x is going to represent theta, sine of theta squared, so x squared, like that. So double check, make sure you get it in there, right? And now to your home screen, I just need math 9, 0 to square root of pi of 0.5 y1 squared d theta. So 3.534. This was worth 2 points. 1 point for the integral, 1 point for the answer. Oh, while I'm sitting here, I'm going to look up how many this was worth. Okay, I just looked this up. This year, the global average for this entire problem was only 2.6. It was only 2.6. So if you got these 2 points, you're already doing pretty good compared to the globe. Okay? All right, so let's see if you can pull out another point and get ahead of that global average. All right. Part B, what is the average distance from the origin to a point on that polar curve for 0 to the square root of pi? Well, the distance is r. That is the distance. Okay? So we want to find the average r. Do we know the formula? We sure do. The average r will be 1 over b minus a. Think of how do you find your average of your test scores? You add them all up and then divide by the number of scores. Well, this is like dividing by the number of scores. You divide by your thetas. and then 0 to square root of pi of whatever you're averaging. So you're averaging r, so we put r in there. Okay, that's going to be it. So calculator time, 1 divided by square root of pi times the integral from 0 to square root of pi of r, which is my y1, d theta. So 1.580 or 1.579. This was worth 2 points. 1 point for the integral, 1 point for the answer. Okay? So I'm hoping that you got at least those 4 points and you were well above the global average. Okay? This year, my students, though, got an average of 3.1 on this problem. So I know they didn't get both of those on average, but I'm sure that there were some people that got that and more. Okay? When I say that the global average was 2.6, that's really pretty low, really low. So know that this was a tough problem. When you tried this on your own, and I hope you tried it on your own, I'm sure you found that there were some tough parts to this problem, and here they come. Okay? Part C. There is a line through the origin with positive slope m that divides region S into 2 regions with equal areas. Okay? Well, I can totally see a line through here that would divide the area into 2 equal areas, right? So it would be something like, something like that maybe. So there's the line, I can see it, that would divide S into 2 equal areas. And we're supposed to write but do not solve an equation involving one or more integrals whose solution gives the area of M. Here's the problem. They don't say there's a line or array theta equals k. That would be easy, because that would be theta equals k. This is not theta equals m either. This line has slope. The line has slope m. So they're saying this line has slope m. I need theta there because my integral is going to go to that theta value. And it's not theta equals m because theta isn't the slope. Theta is this angle, right? Theta is this angle right here. Correct? So I need theta when I only know that slope is m, right? Well, let's take a look at this. What does slope mean? If I drop a perpendicular here, the slope of that is change in y over change in x, right? The slope is change in y over change in x, right? But now look at this right triangle I just now made. Tangent of theta is delta y over delta x, right? So tangent of theta has to be m, because that's what m is. So let's go down here and write it in my area where I'm supposed to write everything. M is equal to change in y over change in x. But that's also what tangent theta is equal to. So tangent of theta must be m. Remember, I'm looking for theta. How do I solve that for theta? Well, I just take inverse tan of both sides. So theta is arctan of m. And now I know what theta is, so I can write my 2 integrals. So the integral from 0 to that theta of 1/2 r squared d theta must equal integral from arctan m to square root of pi of 1/2 r squared d theta. Has to be. Okay? So most of my kids, when they came back that year, they said they did not get that boundary. And they said, what do you think? What would I get for that? And I said, I don't know. We'll have to wait and see. Well, this is what how they scored this. 1 point for what they say equates polar areas. 1 point for equates polar areas. So to me that means the integrand, disregarding the boundaries, are the integrands, even if you didn't get this right, maybe you put an m there or something else, does the equation make sense? Okay, is the equation part right? So I'm thinking mine, they should have been able to do that, right? You guys should do that. You guys should have been able to do that. 1 point for inverse trigonometric function, I'm just going to call it trig function, applied to m as a limit of integration. So did you get arctan of m as one of your limits? And essentially that's what they gave that point for. And then 1 point for the equation. Okay. All right. So yeah, I'm guessing they at least got the 1 point. I'm hoping they would, even though I know the average of them probably didn't. But hey, you know what? Hopefully 1 point out of that is good. Okay, then let's take a look at D. For k greater than 0, let A of k be the area of the portion of region S that is also inside the circle R is equal to k cosine theta. I get it, you guys. It's a confusing statement. Okay? So let's see if we can break that down. And then we need to find the limit as k goes to infinity of A of k. Let's see if we can break this down. We have, let me redraw this, this curve so that I can stay down here. Something like that, right? All right. It says that we want to let A of k be the area of the portion inside S, which is inside here, and also inside R is equal to k cosine theta. Well, this k cosine theta would be helpful if you know that that's a circle out on the positive x-axis of diameter k. So this is a circle out on the positive x-axis of diameter k. Diameter k. So the region that is inside both S and that circle would be this region the way I drew it. So that's the area that's in common. Okay? And they're going to let A, that's our A of k. That's the area that's similar. Okay? Now we want to let k go to infinity. So we're letting this diameter go to infinity. Well, as k gets bigger, what's happening? As k gets bigger, what is happening there? As k gets bigger and bigger, as k goes to infinity, we're getting closer and closer to this area, aren't we? Do you agree? As k goes to infinity, we're getting closer to this area, not this on the other side of the y-axis, but this right here. That's A of k is going to that, right? So the limit as k goes to infinity of that area is going to be the integral from 0 to pi over 2 of our curve, of 1/2 of our curve oh, I should just put squared. I would erase that. I always do the test in the pencils, but for this I like it to show up in a pen. Of 1/2 r squared d theta. Okay? So we have to actually find. So this can go into my calculator. So I have 1/2, integral 0 to pi over 2 of 1/2 my y1 squared d theta. So 3.324. This was worth 2 points. 1 point for the limits of integration, especially that pi over 2, and then 1 point for the answer with the integral. Okay, so tough little problem. I can see why the global average was so low on that. But I'm hoping that you got a few points on that and you can compare yourself with what the global was. And again, my students last year got an average of 3.1 on this. So you can compare yourself to my students from last year, the average student from last year. Okay, let me know what questions you have.